Greetings, the Astro 30 here yet again, and welcome back to AEL. Now, if you're new to this channel, please consider going down below and subscribing if you haven't done so already. Cheers. Today I'm going to revisit this power amplifier schematic, which I did do a video on a few years ago, but never actually built it, mainly because I was in the transition of moving houses and all that sort of jazz, and at the time didn't really have time to look at it properly. However, recently I did some further investigation online because I couldn't find this schematic on my hard drive anywhere. So I had to try and find the schematic again. And through my investigation, lo and behold, I found where this circuit is actually stolen from. It's stolen from, guess where, the Elektor magazine. Now, this is the 1995 UK November issue of the magazine. And this is supposed to be a 300 watt amplifier into 4 ohms. The redrawn schematic by Sam, and he purports it to be 170 watt into 8 ohms, which is probably right. Now, I will want to build this particular amplifier up and test it out, but what intrigues me is there's extra circuitry down here that has been removed on the redrawn schematic. Down here is a protector circuit. It serves two functions. It protects the speaker that's connected to the amplifier from any DC offset, like say one of the output transistors goes away, shorts, and brings one of the power rails up to the output. Well, it will detect that DC, disconnect the relay, protecting the loudspeaker from any further damage. And the second function is it provides a thermal overload protect. So they've got a PTC down here which sits close up to the heatsink bracket of this particular design. And once this resistance value will increase as it heats up, it will then detect that as an overload and then remove the drive to the relay. I'll get to the operation of this circuit in a minute. So the heart of the circuit is using the LM393 dual comparator, and I'm going to look at this side first. Now, I'm thinking the reason why he chose to use a comparator here is for the simple fact is we've got an LED up here which indicates when it's in protect or mute mode, and these three components here is the RC delay constant network. So it's comprised of a 47k resistor, a 47 ohm resistor, and a 47 microfarad capacitor to ground. And we've got a 15k and a 1k5 here on the negative pin of the second comparator here. So this is a voltage divider, and it's actually setting what the input threshold is for the second half of the comparator. So the way this works is the comparator's output will be low when one input is high and the other one is low. But once both inputs are the same or one exceeds the value of the other, then the output will be high. So as this capacitor charges, once the voltage at this point reaches the same voltage potential as the threshold voltage on this pin, the comparator will switch high, which will then turn this transistor on, which will turn the relay on and extinguish the LED. Because when the comparator is in the low state, we now have a path to ground to light the LED. So the reason we probably put the comparator there is because, well, unlike my circuit that I've built using an LED to indicate when it's in the, protect mode, the LED tends to fade out as the base voltage here, if the resistor capacitor network was at the base, before the relay engages. So the LED would extinguish before the relay even engaged, and it kind of looks a little bit, well, strange. So that'd be probably the reason why you'd want to use the comparator. I mean, it is fun to use a comparator. That'll provide our turn-on delay. The next thing we'd want to do is to have an instant turn-off. So we have here these components, these two resistors, this capacitor, this diode, and this transistor. This diode connects to one side of the secondary of the transformer. So it's looking at the negative going cycle. That'll rectify that. So this is a half-wave rectifier. That is then slightly smoothed by this 470 nanofarad capacitor here. And what that does is during the dead time, which is the positive going cycle because it's not being rectified, well, there's going to be a dead spot there. So this capacitor provides a small little charge back into this circuit, which will prevent this transistor from turning on, because this is actually biased on by this 47k resistor to the 15 volt supply rail, which is provided by this Zener diode here. But whilst we've got a negative going AC cycle of 50, 60 hertz, well, it will keep this capacitor charged, which will keep this base low, preventing it from being turned on. As soon as the power is removed, such as the amplifier is turned off, well, this transistor is now allowed to be turned on because it's biased high, which will bring this comparator's input low, which will then turn this transistor off, de-energizing the relay, disconnecting the loudspeaker almost instantly, probably within a few milliseconds or so. The only problem with that is because the 15 volt rail here is actually taken off the amplifier's positive supply rail. So when it's turned off, this LED will illuminate and then it will slowly fade out as the main filter caps discharge. That may or may not be a wanted or desired effect. It's still an interesting concept of how it's been designed here. Now the DC detection part here is formed by this 100k resistor, this 100k resistor, and this 47 microfarad capacitor, and these two transistors. So what this resistor and this capacitor do is it's looking at our AC output from the amplifier, and it's basically shorting out all the audio frequencies to ground via this capacitor. As soon as a DC potential is here, well, it'll either turn on this base of this transistor, or if it's the negative going cycle, it'll come up through this emitter, and as both of the collectors are tied to the same input point of the comparator, basically it's switching ground again to this comparator, bringing this input low. So when there's a negative DC potential at the emitter here, or a positive potential here at this base, well, these transistors will conduct, switching ground up to pin 5 of the comparator, bringing its input low, bringing the output low, turning the transistor off, etc. Pretty simple. On to the first part of the comparator, which is the thermal overload detect. They've got this input here, setting a threshold voltage with heresy feedback using a 1 mega ohm resistor, and they're using the negative input, which is tied high, and we're going through this KTY 81-122 PTC, which is no longer available, it's discontinued. And the resistance of this is around 1K. So as with this comparator, as long as both inputs are high, or even if one's higher than the other, so comparing between pin 3 and pin 2, as long as the voltages on both pins are roughly the same, the output will be high. And we'll notice that there is a diode with the cathode facing the output. So we're looking for when it goes to ground. So being high, this is not going to do anything. This LED will also be off. This is the thermal overload LED, which will illuminate when this output becomes low. And the way that happens is as soon as this PTC gets hot, the resistance will increase, therefore bringing the voltage potential at this resistive divider, which is basically what it is, lower and lower. As the voltage gets lower on this pin, well, it's no longer high like this pin, therefore the comparator switches low. The LED illuminates, ground is allowed to flow through this diode, which is now conducting, which again brings the comparator pin 5 low, which turns the transistor off and de-energizes the relay. So as I said, this part is now discontinued. There are alternatives, but I'm just wondering if I can modify this circuit in order to use an NTC, or negative temperature coefficient, which its resistance decreases with heat. But as long as we can keep both these inputs high, so the comparator's output is high, then messing around with how the voltage divider works here, if the resistance of this lowers, well, we could still probably make one input go low so that the output becomes low and that this circuit still works. So that's something I'm going to be messing around with on this video. But first, what I'm going to do is I'm going to build up this protection circuitry over here and ignore all this first and work on this a little bit later. So I'm going to build this up on breadboard, test it out, see if it functions as it should. I'm going to have to provide a bipolar supply with the positive going to ground here for the negative AC input, so the negative voltage rail comes in here to make this circuit not operate. as well as provide the 15 volts to here and ignore the Xeno diode and the dropping resistor, etc. And then I'll turn to this and see if I can make it work. If I can't, I can't. But anyway, let's get busy. Okay, so I lied. I've actually gone ahead and built the thermal overload section up first. Mainly because I want to correct my explanation of how that part of the circuit worked. It's the reverse of how I said it. The inputs 3 and 2 are actually held low, about 0.7 of a volt with the current values. Because I did some calculations with the voltage dividers and realised it's not going to hold these pins high. I forgot with heresy or positive feedback in a comparator circuit, it flips the operation, so when both inputs are low, then the output is high. As soon as this variable resistor, which is imitating our PTC, is buried and the resistance is starting to get greater, well, the input potential voltage at pin 2, which is what it's looking at, will start to increase, allowing the LED to light. So it should be pretty simple to reverse this around, so we're actually looking at an increase in voltage difference between here. So what I propose to do is I'll replace this fixed resistor with the NTC, or a pot in this case, make the value of this resistor the same, leave this as 1K5, make this value of R, which is our PTC currently, the same as this value, so both inputs are roughly going to be the same voltage, and then, well, I've got a 5K pot at the moment, so I'll change this to 4K7 and then vary the potentiometer until we get the same voltage and see if we can get the same results as when we reduce this resistance, that the comparator will turn to the low state. The voltages at these two pins will be different with the different voltage divider values, but that's fine. So let me get to messing around with the circuit and see if I can make that happen. Well, with the circuit modified around, I've now got a 4K7 time pin 3 high, 1K5's time both inputs low, and the 5K potentiometer on pin 2 of that comparator IC set to the full 5K. So this value is actually higher than the 4K7, but if I rotate the pot, as the resistance decreases, the LED lights up. We're at 0 ohms now and it's solid lit, so yeah, that was easy. So what I really need to do is change this 4K7 to a value that's going to be similar to the NTC, which I've got a 10K one sitting around somewhere, and we'll just use a NTC instead and then just muck around with the values until, well, it's given me the desired operation. I've got the NTC in circuit there, and I've left the 4K7 at its current value. I'll just take the tip of my hot soldering iron and touch it close to the NTC, but not close enough to melt the epoxy, and we'll see if the LED lights. So I'm going to have to come around the camera because it's kind of in the way. This may take a while, because I'm not actually sure how much heat is. There it goes. Nice. So I'm not sure what temperature that will actually be experiencing, but as we can see, once it heats up enough again, if I can get this to operate again, it'd be nice. There it goes. So yeah, that does work. My iron is apparently 360 degrees Celsius. So I'm not sure what temperature we're getting to. So in the end, it might be advisable to, the LED just went out, might be advisable to probably make this resistance value close to that resistance value of this, which is 10k, because in other words, this resistance value here on this input has to be higher than the resistance value there for this to obviously work. But I think 4k7 might be going a little bit too slow in reaction. So I don't want to put it at 10k because it's too close to its current value of the NTC. So I might go at 8k2 for the pull-up resistor. So I'll just pull him out of circuit. I could put a potentiometer there, but I don't really want to do that. Am I actually going to include this circuitry on the final design? Maybe. So as we can see, with pin 3 tied high, we're actually got solder all over the thing. Well, it's now turned back off again, which is fine. So I'll bring the soldering iron in. There it goes, it's starting to illuminate, and it's full illumination. So I've got an 8k2 there at the moment. Take the heat away. So I'm not exactly 100% sure what values I want to use. I could use a higher resistance of NTC there and get a longer, like you know, turn on transient there. But as soon as that NTC cools, well then it should extinguish again. Well, that's the theory anyway. I'll blow on it. Maybe not. I touch it with my fingers. Yeah, it went out. So obviously the temperature of my skin is a lot lower than the temperature of what the iron was putting into it. So the circuit works. Yeah, okay, it could be fiddled with a bit more. But now what I should do is what I was going to do in the first place, which is turn my attention to the protection side of the circuit. It's actually the next day, because I ran out of time yesterday. I've gone ahead and I've built this part of the comparator circuit from the delay capacitor, I'm going to call it, forwards, and I just haven't built any of the stuff that way backwards. That'll be next. But I wanted to test the comparator, the delay time and everything with a relay. And the circuit works, so there it is there. That's the LED to indicate the protect state. So I'll turn the circuit on. There is, however, two slight problems. Well, the first one's not really a problem, but the first thing is the delay between when the relay came on was pretty short. It was only like about 2 seconds. I could mess with the voltage divider resistors on pin 6 of the comparator to change the threshold voltage, or I could just simply increase the value of the capacitor here. Currently it's a 47 microfarad. I could probably use 100, get a better delay. I'll investigate that in a second, but the second problem is, I don't know if you can see that, but that LED is glowing dimly. And it's most likely because of a leakage current through the base emitter junction of the driver transistor there. Because if I turn the supply off, see, the LED went out completely. So that's kind of an issue. If I used a high intensity LED there, it'd be still pretty bright. So I've got this fly wire connected to pin 5, I believe it is. Yep, which is our offline. And if I bring this to ground, well, the relay drops out and the light lights back up. So what I want to do first is I want to change the value of this capacitor to see if I can make it, you know, a longer delay. Secondly, I want to fix this LED, because as I said, there might be a leakage current through the base emitter junction of this transistor here. I'm currently using a BC546. I don't have a BC639. I could try putting another transistor in, like a PNP transistor in place of the LED where it is, and then from its collector to ground run the LED. That'll probably be the easiest solution. Alright, I've got a 100 microfarad capacitor in there instead. That's probably a bit too long, to be honest. So I'll bring this to ground. 2, 3, 4, 5. That was about 5 seconds. Well, I could change the value of the 470k that's there instead, as well as, I should say, just to bring that down a bit. I might try a 330k. So, and then I'll fix the LED issue. I'm just shorting that out to make sure that capacitor gets discharged. Okay, I've got the 330 in. So, 2, 3, 4. That's a bit more respectable. So I'll just bring that to ground again. 1, 2, 3. Yeah, that's about right. I'm going to stick with those values. That seems to be the best at the moment. And now on to addressing the issue with that LED. Sometimes the best solution is the simplest. I've just added a diode between the output of pin 7 of the comparator before the driver transistor. So we're actually isolating this transistor completely from this circuit. And now the LED goes out completely. Currently the LED is off. I ground pin 5. LED is on. Goes out. And it is not glowing at all. And I destroyed an LED in the process. I was mucking around with the circuit with it turned on, which is never a good idea. I just want to find where my blue LED is because it's brighter. And I'm going to swap out the LED and see if we do actually have any leakage current, or I have actually solved the issue. I've solved the issue. So that's going to be pretty bright when I do that. So that's fine. So that's that circuit fixed. So we know now there should have been a diode there. So I spent the last half an hour pissing about with transistors, which didn't work, by the way. And it was starting to get to the point where the circuit was starting to get more complicated than necessary. So I've changed that and put a simple solution in, just an extra component, a diode. So now I can move on to the next part, building up this front end part of the circuit. I'm not going to worry too much about building this loss of AC detection circuit. I'm just going to build the DC detector, see if that works. I don't have a 47 microfarad 50 volt, but I've got a 100 microfarad 50 volt non-polarized. So it will take a little bit more longer to react to DC with the larger capacitor, but it's good for just testing purposes. And then I'll worry about testing this part of the circuit, and then I'll finally redraw all of this to show you what's been changed, and for modifications. And I'll also let you know that I'm changing the transistors from BC337s to 546, because why not? They're a better transistor anyway. So let me get to fleshing this part of the circuit out now, and once I can find a spare bit of breadboard, and we'll test it further. Something that is so simple seems to be the most difficult to get to work right. I've built the DC detector. I blew the crap out of one of the transistors because I just put the voltage directly at the base of the transistor for testing purposes because it wasn't working, and it didn't like that, it just blew up. But pity I didn't catch that on camera, it would have been funny. It is working now because it helps to connect the two collectors to pin 5 of the comparator, not pin 6 where it was. Now it works. So this wire floating around here is my input wire, which would come off the power amp normally. That's going to the one end of the 100k resistor that goes to the base and emitter junctions of those two transistors. So I touch this between positive or negative. I've got a negative supply voltage of about 19 volts on this side at the moment, which is fine. Again, that was ramped up for testing purposes. So I now bring the base to positive, There we go. Remove it. Resets. Negatives is a little bit slower, but it does work, which is good. Okay, reset. So now I will just leave it connected to negative. I'll check the one that's responsible for negative, make sure the transistor's not overheating or doing anything stupid. No, it's not getting hot. Alright, I'll swap to positive. Nothing's happening. Excellent. And that should reset now. And there it goes. Okay, so faffing around for the last hour trying to just get a simple 2 transistor, 2 resistor and a capacitor circuit to work. I also realised I put the LED for the overheat detect on the anode side of that diode. It should have been on the cathode where it is in the schematic. I've reversed those connections round. I have tested it and it works. This comparator circuit is actually now connected after the anode here to pin 5 over there. And well, next thing I'm going to do is we'll heat it and test it. But then I'm going to build up this part of the circuit which was remaining to finalise the testing. And that's what I need the negative 19 volt rail that I've got currently for. So the best source of heat is the soldering iron. Now we know from a previous test that the soldering iron, or that part of the comparator circuit, did work. I just want to make sure it still does after I change the orientation of that LED. Yes, it does. But I still think that that 8K6, I think it is now, that's in the pin 3 of the comparator is too high. It needs to be a lower value because it's reacting a bit too quick. And today my fingers are too hot in order to make that go off, so a bit of free spray helps. Excellent. So that's that part of the circuitry all working nicely. With that AK6 it'd probably be better to have a 10K trimmer pot there instead. As I say, I'll redraw the schematic at the end and we have a look, see what I've changed. This is neither here nor there. I wonder if that will react with my finger, out of interest. Yes, it will. Okay, so let me get to building the loss of AC detection part of the circuit, which I'll put over here, and we'll test that next. Okay, I think that circuit is wired correctly. I haven't tested it yet. So there's our rectifier diode, which is going to the negative rail, which is the incoming 19.6 volts, and that's going to be our AC for the test. And the collector of that transistor goes back to pin 5, but I had to wire it all the way over with a long wire to the collector junctions of these 2 transistors because there just isn't enough pins left open where pin 5 is. It's messy, but anyway, so I'll give it the positive supply, and well, it turned on. Ah, I know why, because I haven't got, no I do, I thought I didn't have the 47K going to the base to the positive rail, but for some reason it's not. I know why, because the emitter's open. I'm an idiot. Always, every time I build a transistor circuit, I forget to connect the emitter to something. Every single time. That's what happens when you rush. So, if I can work around the camera here, I will plug in this wire, which is going to ground, and the circuit goes off. That's what it's supposed to do. Okay, so I now know that that's holding the comparator's pin 5 down low, so the circuit is currently muted. So if I turn the other supply on, not much is happening. Not much is happening. In fact, nothing is happening. Well, that's disappointing. I mean, the supply voltage is probably too low for a start. I might change the 120k out for something else lower, like 100 or even 47, so they're both even, just for this test. Well, there's another dead LED. Blew that one up when I was fiddling around with the changing of resistors there. I still had that part of the circuit powered up and it shorted on something. It's gonski, so now I'm down to just 2 remaining green LEDs of that range. I'm going to have to buy some more. Okay, so currently we're got a even voltage divider of 47k each, which I may actually leave like that. So if I turn the negative supply on, wait a few seconds, there it goes, and that's what that circuit's supposed to do. So that is working. I'll just verify that the DC protector is still working, which it is. There we go. All well and good. I mean, I don't think it would hurt for it to be 47k, to be honest. So I might leave it like that. I'm just going to see if this will... There it goes. Excellent. So thermal overload is working with it. And there we go. Excellent. So that circuit is working, even though I had to make a few modifications. But let me get to drawing the schematic out on a bit of paper, and so it's nice and clear, and we'll have a look at what is occurring. Okay, please excuse the crudity of this drawing. I didn't have time to draw it to scale or even to paint it. Yeah, that joke is starting to get very old. Damn you, Dave Jones. Anyway, as messy as this looks, it just shows what my changes are. So I'm using an NTC, negative temperature coefficient, here as our temperature sensor. I've decided with the voltage divider network here to make pin 3, which is our threshold voltage, a variable resistor of 10k. So this value here has to be lower than that value there. So, and that's at room temperature, by the way. So this will not be 10k if room temperature is above 25 degrees Celsius, for instance. It'll be a little bit lower. So this value needs to be lower than what the actual base resistance of this is, or else the circuit's going to false trigger. So that's why I decided to opt for a little trimmer here, so you can trim it down to get like a resistance of like 4k7, 3.3k, etc. So you're setting the threshold voltage here higher and higher, and so when this actually heats up, well, this voltage is going to get higher and higher at pin 2, and once the voltage at pin 2 is higher than the voltage at pin 3, so it's unbalanced, this will switch low, the LED will light, and then it will drive the rest of the circuit to turn the relay off. Now I haven't shown the relay or the dropper resistor. That goes in between this point and the VCC line of the power amplifier, with a dropping resistor in between, calculated for the current of the relay being used and its voltage, as well as working out the power with power versus the current being drawn. So I've just kept it simple by not showing that, because there's various different relays that could be used. So VCC comes in through RZ, which is our dropping resistor, which on the original schematic is a 3K3 5-watt device, which comes off of VCC, goes into this 15-volt Zener, which is supposed to be a 1.5-watt Zener. Don't know why. A 1 watt would work just fine. So that gives us our 15-volt rail here. Not much has changed here, except for our delay constant. I've gone 47k. Sorry, I'm looking at the wrong thing, aren't I? 330k. I left that 47 ohm there, which I don't really know why it's even there. I don't know. And a 100 microfarad capacitor. This comparator is the same. Our AC detection has been changed slightly. I've gone 47k for the base pull-up resistor and 47k for the pull-down resistor to ground. That's marked as 47 microfarad, which it should not be. That's 47 nanofarad. That's a bit better. I got confused when I was writing a 47 there. I was thinking it was the delay capacitor. Whatever. And there's a 4004 diode, which is rectifying the negative incoming AC. As with this comparator here, pin 7 is going through a 4148 signal diode before the relay driver transistor, so that this LED isn't illuminated dully all the time. I don't know in his original test, Circuitry, whether he noticed that or whether it doesn't do it at a higher voltage, but nonetheless I'm including the diode. So other than that, this detector circuit over here worked perfectly first time when I actually wired the collectors to pin 5 and not pin 6. So yeah, that's good. That's it. That's this circuit tested and modified a little bit, just so we can use more modern components and also get rid of that PTC that's going to be a bastard to find a good one of, because they're obsolete now. And yeah, box of birds. So I'm happy that this circuit worked, and worked relatively first time, even though I've blown up, what is it, 2 LEDs, 1 transistor. I think it's 2 LEDs. Yeah. But I can't find the transistor now because I threw it in the bin, but I was going to show you how it just actually blew the side of the silicon clean off the transistor. But the circuit is still powered up next to me and is still working, so I'm happy with that. So, tell me your thoughts below. Should I, when I'm building the main power amplifier, when I breadboard it up and test it obviously, when it comes time for me to make maybe a PCB for it, if I decide to go that far, do you suggest that I include this circuitry just to keep it like for nostalgic reasons from the original amplifier, or to leave it off? So leave your thoughts below, and I'm going to end this video here. I'm the Astro 30, and if you enjoyed this video, please remember to go down below, like, comment and subscribe if you haven't done so already. And as always, this is the Astro 30 saying see ya, thanks for watching, have a great day.